Okay, this is our Thursday lecture, the 22nd of April, and this is our last asynchronous lecture of this semester. Today we're going to go into some practical applications of flux and changes in flux and induced currents as applied to power generation and power transmission, with a little bit on inductors at the end. So we'll start off with a quick review of Faraday's law. Then we'll get into generators and transformers. Okay, you probably heard of both of these, but you may or may not have discussed what they do and how they do it. And then we'll get into inductors. So Chapter 30, sections 30.1 and 30.8 are what's on the exam. In homework 12 I posted, and you do not need to do this. You don't need to turn it in, but you need to do it because you're responsible for the material on the final exam, and I've posted the solutions. And so the final exam again is on Wednesday the 5th at 2 o'clock online. And remember, based on the syllabus, that the final is cumulative, and I do drop your lowest exam score from the 3-unit exams and the final exam. All right. So let's do a quick review. Yesterday we covered Faraday's law. And Faraday's law, remember, if you have a changing magnetic flux going through a loop and it changes with time, that generates an EMF, an electromotive force. Okay, in practical terms, a lot of times an electromotive force is referred to as a voltage. Okay, so it generates a voltage difference, a potential difference through the loop, and that loop induces a current, which is the EMF by Ohm's law, EMF over R, and the direction is given by Lenz's law. Okay. Now, if we have N turns in the coil, we just simply multiply the change in the flux through each term by N, and you can get a much larger EMF in a coil. Now, typically what we do in practice is we calculate the absolute value of the change in flux, and that gives us the absolute value of the EMF. And then we use Lenz's law to get the direction. Remember, Lenz's law says that the EMF is induced such as to oppose changes in the flux. Okay. Now, mathematically, we can write this as, instead of the absolute value and then doing Lenz's law, we can write it as the EMF is negative time derivative with respect to flux. It's the same thing as doing the absolute value and then using Lenz's law to get the sign. So this mathematically, we'll see this today and when we're talking about generators. So this is just another way of combining Faraday's law, which is getting the magnitude, and then tacking on the negative sign based on Lenz's law. So if you look at the definition, remember the definition of the flux through a coil is it's the magnetic field strength through the coil times the area of the loop times the angle that the tilt that the coil makes with respect to the magnetic field. Okay, and if B is not constant, then we have to integrate this flux. So you get maximum flux when the magnetic field is hitting the coil straight on, right, where the angle between the area vector and B is 0, so cosine is 0, and you get minimum flux when you tilt the coil 90 degrees with respect to the magnetic field. So if we want to change the flux based on this equation, we either have to change B, which means increasing the field strength. We need to increase the area of the loop, or we can tilt the loop. We can turn the loop so that theta's changing with time, and we'll see that that's how generators work when generating electricity. So there's 3 possible ways that we can change the flux through a loop. And remember, it's the changing flux that generates the EMF, not the value of the flux. So there's Lenz's law. So let's apply this to Faraday's law to a generator. Okay, so here's a generator, and this is what's called an AC generator. It generates an alternating current. Okay, and this is, for example, at the power plant here. So you have a big magnet. You have the North Pole and the South Pole, or magnets that make this large magnetic field. And then you have a big coil of wire. Okay. And if you turn the coil, so for example, if the coil is spun by some mechanical source, like a windmill that turns this coil, or flowing water from a dam that turns the coil, what that does is it rotates the coil, and then the angle of the coil with respect to the magnetic field changes with time. Okay? And so this device converts mechanical energy, which comes from the flowing water or the windmill, etc. It converts mechanical energy into an electrical energy, and a device that does that is called a generator. Okay? And so let's take the flux, and we can write, if the coil is rotating with some frequency f and an angular frequency, remember 2 pi f, that's radians per second, we did that in 1150, then the angle theta can be written as omega times t. And so we can take the flux, which is n number of turns times BA times cosine of theta, but we plug in omega t for theta. And the mth is the negative time derivative of this. Okay. Now, if the number of turns is constant, we can take that out of the derivative. If b and a are constant, we can take those out, and we're left with this expression here. And the derivative of cosine omega t is negative omega sine of omega t. Your negatives cancel, and we're left with the equation of the mth induced in the coil. And if you look here, the mth induced by a coil varies as a sine wave with time. And so if you plot this, it varies as a sine wave at the frequency that the coil is rotating. And in power generation in the US, that's at 60 hertz. So this coil is rotating at 60 cycles per second, and that generates a potential difference in mth that's a sine wave at 60 hertz. And you see that since it's a sine wave, during the first half of the cycle, the mth is positive, and the second half it's negative. And so the current is also positive in the first half and negative in the second. And you get a current that's a sine wave, and we call that alternating current, since it goes from positive to negative to positive to negative, etc. And that's typically denoted as AC. So you've probably heard of AC power or AC voltage, okay? That's just alternating current, okay? And we can see, if we take a quick look here, why that is, okay? So suppose that your coil starts here and it starts to rotate toward counterclockwise, okay? In the first half of the cycle, the flux is going to be increasing in the loop. And then the second half of the cycle, the flux is going to be decreasing in the loop. So it goes increasing, decreasing, increasing, decreasing, and that's what gives rise to this alternating current. And so this is how AC current and AC voltage are generated at the power plant, is by this big coil rotating in a large magnetic field. And so you should be able to derive this on an exam. You should be able to plug this into Faraday's law, take the derivative, and show that the mth in a coil varies sinusoidally with time. And the magnitude of the mth depends on how fast the coil is rotating, the number of turns, how strong the magnetic field is, and on the area of the coil. Okay. So by having fairly large areas and moderate strength of the field, we can generate large potential differences. So here's an example. So suppose that you have a given generator and it has an 18 centimeter diameter coil, and let's make it with 120 turns. So N is 120. And suppose that it rotates at 60 hertz in a uniform magnetic field perpendicular to the rotation axis. Okay, so in other words, it's a picture that looks like this. Okay. So the question is, how strong of a magnetic field do we need to generate a peak voltage of around 170 volts? And this is typical of the residential voltages. The peak of the sine wave is 170, and what's called the root mean square value, which you can kind of think of like an average value, is 120 hertz, 120 volts, and that's what comes into our house. Okay, so let's plug this into Faraday's law. So we plug it in. Okay, we take the derivative. Remember, N times the change in the flux with time, and then since A and B are constant, that's just the changing because of the angle, and then we get our expression that we derived. Okay, now if we know that the frequency is 60 hertz, we can get omega's 2 pi f is 377 radians per second. And if we know that the diameter is 18 centimeters, well then the radius is 9 centimeters, and we can calculate pi r squared as the area. And then we plug in 120 turns, 170 volts, and we get that the magnetic field strength needs to be 0.15 Teslas. Okay, that's how strong of a magnetic field you need to generate 170 volts peak sine wave, given the coil dimensions here. And this isn't a huge value for magnetic fields, and so you can generate pretty large voltages with pretty moderate level magnetic field strengths in a decent sized coil. Okay, so you should again be able to apply this on an exam. So that's all fine and dandy, but now this power from the power plant, so here you got your big generators here, and they're generating a voltage, and now this voltage needs to be transmitted large distances to your home. Okay. Now there's one problem with this. If the current is not low, remember that the heating in a wire is I squared R, right? And so if we transmit this at large currents, we're going to lose a lot of energy due to heating of the wires, which we don't want, okay? So to minimize this loss in energy, we want to step the voltages up to very high voltages at very low currents, okay? Remember, the power is the product of I times V. And so we can transmit the same power at a high voltage and a low current, or at a low voltage and a high current, right? And so typically it's always desirable to transmit it at a high voltage and a low current to minimize the amount of heat that's lost in the wires here, dissipated, okay? Now that's all fine and dandy, we transmit that, but the problem is now you get down to your house and most of your appliances, this voltage is too high to be practical. So we need to step this down to a lower voltage, okay? Lower voltage at a higher current, okay? Now how do we do this? We change the voltage using these devices called transformers, okay? And transformers are devices that change the AC voltages, okay? So here you've got what's called a step-up transformer near the power plant that increases the voltage, decreases the current, and then the power is transmitted, and finally we need some step-down transformers which turn down the voltage, albeit at a higher current. And you've probably seen these, right? You've seen these transmission lines, and you've seen these transformers. The purpose of these is to change the voltages, to transmit efficiently, and then to bring it down to levels that are better suited for residential power usage. So how do transformers work? Okay, well, you have two coils. first coil is what's called a primary coil, and you wrap that around an iron core or a magnetic material, usually iron. And you take the second coil and you wrap that around the other side of the magnetic core. Okay? And here's your two wires. And so the input voltage or the input current, which is called the primary voltage and the primary current, that comes in here. And what's that going to do? Okay, well, that's going to generate a large magnetic flux, right? Because you have a large current going through this coil, and so that's going to generate a large magnetic field, which means a large flux, okay? Now, the purpose of this iron core here is to trap all of the flux in the iron here, so that it all gets coupled to this secondary core. So in other words, we don't want to lose any of this flux. We want to make sure that the field lines all get curved and transmitted, and so they go through this secondary core. And that's the reason that you have it wrapped around this iron core, is to sort of trap the flux inside the core. Okay? Now if this current were a DC current, you'd get a flux, but you wouldn't get any changes in flux, right? And so you might get a large flux through this secondary coil, but it wouldn't be changing. And so Faraday's law says that if the flux isn't changing, you don't get any voltage here. Okay? Now, if the flux here, since this primary voltage has a sine wave and it's changing, now you've got a large voltage, a large current here, which is changing in time, and that produces a changing magnetic field, which produces a changing flux through this second coil. And that changing flux generates an EMF, and so we can generate a voltage in the secondary coil. And the whole purpose, we'll see in a minute, if you play games with the number of turns in the primary and the secondary coils, we can either turn the voltage up or we can turn the voltage down, okay? Remembering that if the voltage gets increased, the current is decreased, and vice versa. Here's a small transformer that you might see in a commercial device, okay? These also work, you have your little power supplies that you plug your laptop in, and some of your consumer electronics, they all have transformers in here. And the purpose of the transformer in this case is usually to knock the voltage down from the 120 volts coming in your plug down to about 5 to 12 volts for your electronics devices. Okay, so any power supply that you plug into the wall, you've got a transformer in there. Okay, and here's an example of one. The primary windings are black, and the secondary are a different one, different color. In this case, green. And so what we want to do next is we want to derive an equation which relates the primary voltage, meaning coming in, to the secondary voltage, which is coming out. Okay. And the key point in doing this, we're going to apply Faraday's law, is that the magnetic flux through the primary coils all gets transmitted to the secondary coil. None of it is lost. And so the flux through this coil, which we'll call phi primary, is equal to the flux through this coil, which we call phi secondary. Okay? And if the fluxes are the same, then the rate at which they're changing with time is also the same. Okay, so fine. What are we going to do with it? Okay, well, the EMF in the primary coil then, so the EMF is, we'll call this the EMF is voltage, right? So the voltage in the primary coil is the number of the turns in the primary times the change in the flux of the primary. Okay, the rate at which it's changing with time. And the secondary is equal to the number of turns in the secondary coil times the change in the flux through the secondary with time. Now we've said that these are equal. So we're saying that the flux through both coils are equal. So these are equal, and if we set these equal, we get that the ratio, we divide this side by NP and divide this by NS, then the change in flux is the same for both, and we get that VP over Vs is equal to Np over Ns. So what that says is that the ratio of the number of turns in the primary coil divided by the number of turns in the secondary coil is equal to the ratio of voltage here divided by voltage here. And so let's just suppose as an example in this coil, let's just say that the number of turns in the primary coil is twice as many as the number in the secondary. So Np divided by Ns would be 2. That means Vp would be 2 times Vs. In other words, the voltage output would be half of the voltage input. And so based solely on the number of turns in each coil, that can be used to design a transformer which either steps up or steps down the voltages by a given factor. Okay, in this case it steps down the voltage because the output voltage from the secondary is smaller than the input through the primary. Okay, so that's fine. Now remember that the power in, which is I primary times V primary, must be equal to the power out, which is I secondary times V secondary. And that's assuming that we don't lose any power, which in reality we always lose a little bit. But for an ideal transformer, power in equals power out. So let's set Vp times Ip equal to Vs times Is. And what you get is that the ratio of the voltages, Vp over Vs, is the inverse of the current. Okay? And now we have our relations here between the number of turns in the coil, the voltages, and the currents. Okay? So in this particular example, Np is greater than Ns. So Vp would be greater than Vs. In other words, we're stepping down the voltage. But Is would be bigger than Ip. So we're stepping down the voltage, but we're increasing the current so that the product of current times voltage has to stay the same. So we can choose with our transformer to either step down the voltage and step up the current, or step up the voltage and step down the current. So at the home, before the power comes into your home, we step down the voltage and we step up the current. And so there's a couple examples, 11 and 12 in your homework, which give more examples with this. This is a very simple equation once you've done an example or two. So here's another picture. Remember, if the number of secondary turns is greater than the number of primary turns, then we go back here. Then N secondary bigger than N primary. This number is less than 1, which means the secondary voltage is bigger than the primary. And so in this case, we're stepping down the voltage. Okay. If the number of secondary turns is greater, the secondary voltage will be greater. Oh, that's a step up, I'm sorry. If Ns is greater than Np, then Vs would be greater than Vp. So now we have a step-up transformer, which increases the voltage at a lower current. This high voltage goes through the power lines here, these transmission lines, gets down to these transformers near the home, and these are step-down transformers. Step down just means that this should be Ns is less than Np. My bad, I'll fix that. Ns is less than Np, which reduces the voltage and increases the current. Okay. So now you've got 120 volts AC coming into your home, and now your electronics that you plug in, a lot of those need only 5 to 12 volts. Furthermore, they need DC voltage, so there's a few other things in your power supply to convert AC to DC. But the first thing is a transformer, and then in this case you want to step, for example, 12 volts. If you want a 12 volt supply, we would have V primary as 120, V secondary is 12, which means you need a transformer with a ratio of turns of 10 to 1, 10 turns of primary for every 1 of secondary, and that will knock your voltage down by a factor of 10. Okay. So you should be able to, on the exam, apply this equation for transformers to relate the number of turns to the voltages and the currents coming in and going out, primary, secondary. So let's stop for a second, and I want to show you a pretty good YouTube video which kind of summarizes generation of electrical power at the power plants and this transformer. So we'll stop here for a minute and watch the video.
Easy reach. Whether you want to vacuum the living room or recharge your phone, all you have to do is plug into the wall and bam, instant access to electricity. But have you ever wondered how all of that electrical power gets to your house, school or office in the first place? There are lots of steps, but two of the most important ones involve electric generators and transformers. And both of these devices work because of a concept we introduced last time, induction. Electric generators are like the opposite of electric motors. Motors take electrical energy, so the current running through a coil of wire, and convert it into mechanical energy as the motor turns. Generators, on the other hand, take mechanical energy, the rotation of a coil of wire, and use induction to convert it into electrical energy in the form of a current running through a wire. Generators use a wire wound around something called an armature, basically a cylinder that rotates within a uniform magnetic field. As the loop rotates, the changing magnetic flux induces a current in the loops of the coil. But the angle that the coil makes with respect to the magnetic field keeps changing, which causes the direction of the induced current to reverse itself at every half turn. So the magnetic field in the generator stays constant, but because the coil is rotating, the angle between the coil and the magnetic field changes. This means that the magnetic flux through the loops in the coil changes over time, which is what induces an EMF. And as we'll soon see, the EMF depends on the sign of the angle between the coil and the magnetic field. So for half the rotation, the sign of the angle is positive, and for the other half, the sign of the angle is negative. When it's positive, the current flows in one direction. When it's negative, it flows in the other. This means that the direction of the current flips with every half rotation. This produces a type of flow of electricity known as alternating current, or AC. And until now, we've mainly been talking about DC, or direct current. There are DC generators which include special parts to make the current keep flowing in the same direction the whole time, instead of reversing itself as the coil turns. But AC power is the kind that flows from the outlets in your walls. And in most places in the world, it reverses itself either 50 or 60 times per second. This is called the frequency of the current, and you'll normally see it written in hertz. Now we can calculate the strength of the EMF in a generator using some of the principles we talked about last time. We've already described what happens when you move a loop of wire in or out of a magnetic field. The EMF induced in the wire is equal to the strength of the magnetic field times the length of the loop times its perpendicular velocity. In other words, it's the velocity times the sine of the angle between the magnetic field and the loop. And the same idea applies to a coil of wire rotating in a magnetic field too. We just have to replace some of the variables with ones that apply to a rotating coil. First, instead of the length of the loop, we'll use the area of one loop of the coil, A. And instead of translational velocity, we'll use angular velocity, omega. Next, the angle theta is just equal to the angular velocity, equal to the number of loops in the coil times the strength of the magnetic field times the area of a loop of the coil times the angular velocity times the sine of the angular velocity multiplied by time. It's a bit of a mouthful, but that's because there are so many factors that affect the EMF induced in the coil. Basically, the equation is saying that you'll have a greater induced current in the generator if there are more coils in the wire, or if there's a stronger magnetic field, or if each loop of the coil is bigger, or if it rotates faster. Now, it might seem kind of strange to have a generator produce a current that reverses itself dozens of times a second, but actually this is incredibly useful. That's because another important device that gets electricity from the power plant to your house is a transformer, which is made up of two coils of wire. And transformers only work with AC power. They're necessary because one of the problems with transmitting electricity over long distances is that if the voltage is low, a lot of power gets wasted as heat. We're talking like 80% in some cases, which is a huge waste of energy. When electricity is transmitted at higher voltages though, much less power gets wasted as heat. That's because for the same power, a lower voltage translates to a higher current, and power loss increases proportionally to the square of the current. In other words, if you double the voltage, you end up with only a quarter of the power loss you had had before, and if you triple the voltage, you get a ninth of the power loss. So it's worth transmitting electricity at very high voltages. But then you need a way to change the voltage of the electricity running through the lines from its original voltage from the generator, which could be around 12,000 volts, then up to a very high voltage as it travels long distances, which might be as high as 240,000 volts. That's definitely not safe in your household appliances. So once the electricity gets where it needs to go, you need to lower its voltage again. In the US, the power coming out of your wall is 110 volts, and in most other places, it's 220 volts. All those voltage changes are made using transformers, which take advantage of something called mutual inductance, where a change in the current in one coil leads to a change in EMF in another nearby coil. An EMF is the same thing as voltage. This change happens because the changing current in the first coil produces a changing magnetic field. So the magnetic flux through the second coil changes, which induces an EMF. And the EMF induced in the second coil will be equal to the changing current in the first coil divided by the change in time and multiplied by a constant m. M depends on things like the size and shape of the coils and how they're positioned relative to each other. This works in the opposite direction too. A change in the current in the second coil will induce the corresponding EMF in the first coil. In transformers, the power running through the first coil is AC, which means the current and the magnetic field it produces are constantly changing. So an EMF is induced in the second coil. But if the second coil has more turns than the first, it will have a higher voltage and vice versa. Here's why. Faraday's law, which we talked about last time, says that the EMF or voltage in each coil is equal to the number of loops in the coil times the change in magnetic flux over time. We can write this out as an equation for each coil separately, using a subscript P for the primary coil and a subscript S for the secondary coil. Now, we want to know how the voltage in the secondary coil compares to the voltage of the primary one. To find out, we divide the voltage in the secondary coil by the voltage in the primary coil. The change in magnetic flux over time cancels out, which leaves us with a simple but useful equation. The voltage in the secondary coil divided by the voltage in the primary coil is equal to the number of loops in the secondary coil divided by the number of loops in the primary coil. So if the secondary coil has twice as many loops as the primary coil, it'll have twice as much voltage. And if it has triple the loops, it'll have triple the voltage, and so on. If the secondary coil has more loops than the primary coil, so that it increases the voltage, that's called a step-up transformer. And if it has fewer loops than the primary coil, so it decreases the voltage, that's a step-down transformer. As the electricity in power lines travels from the power plant to your house, it goes through lots of step-up and step-down transformers. If you've ever seen a Tesla coil in action, that's just a fancy version of a step-up transformer. The secondary coil is designed so that it shoots out bursts of electricity that look like lightning bolts. Mutual inductance is also used in lots of other things too, like wireless chargers, for example. Lots of cell phones have a wireless charging feature where you just put the phone on top of a charging pad and it charges. No need to plug anything in. It works because there's a coil inside the charging pad and another one inside your phone. The AC power running through the charging pad induces an EMF in your phone's coil, which can use the energy to charge its battery. So the same technology that helps get electricity to the outlets in your wall can move power from one device to another, even if there are no physical connections between them. Today you learned about how electricity is produced and transmitted. We explained how electric generators worked and derived the generator equation. We also talked about transformers.
Okay, so that was a nice little summary of power generation and stepping up and stepping down voltages using transformers. You should be able to apply Faraday's law like we said in an example 1 to show how the coil properties right here are related to the EMF generated. You should be able to apply that. You should also now be able to apply the equation for transformers to relate the number of primary turns in the primary coil to the secondary turns in the secondary, and you should be able to relate that to the primary and secondary voltages and currents, and explain how transformers are used to step up or to step down the voltages. So the final topic that we're going to cover in the course is inductors, okay? And so an inductor is pretty similar. It again is a coil of wire, and it relies on the fact that a changing flux through the coil induces a potential difference, an EMF, okay? And so far we haven't discussed that in any circuits. This is used in circuits. So far we've discussed circuits containing resistors and circuits containing capacitors. And remember, resistors dissipate power, right? And their resistance is the potential difference across the two terminals. divided by I, and that has a unit of an ohm. Capacitance, remember capacitors are used to store charge, right? And hence they store energy in the electric field between the plates. And their capacity to store charge is equal to the charge Q on each plate divided by the potential difference. And that's called the farad. So we've discussed circuits containing capacitors and resistors, okay? The third circuit component, of course, in addition to batteries and some source of energy, batteries, or in this case generators, is what's called an inductor, okay? And we denote the inductor with the symbol L, just like the capacitor has the symbol C. And so the inductor is characterized by a property called inductance, okay, just like a capacitor has capacitance. And the inductance is equal to the magnetic flux that is in the flux going through the coil divided by the current. So it's the ratio of the flux to the current, okay? And so just the units here are really weird. They're called henries, okay? Because flux has units of Webers divided by amps. Okay, well, Weber amp, what's that, right? So Weber, remember, flux is magnetic field strength times area times cosine, so Tesla times meter square over amp, and we call this goofy unit the Henry, and we denote that with the symbol H, okay? I promise this is the last new unit for the semester. So just like capacitors are used to store energy in the electric field between two plates, inductors are used to store potential energy in the magnetic field of a coil, okay? And so they play a role analogous to capacitors and complementary. So here's a coil, and what happens is when you have a current going through, remember a current going through a solenoid, that generated some magnetic field, which we studied in chapter 29. Remember, the field depends on the current through the coil times the number of turns divided by the length. And so you get this uniform, strong magnetic field in the coil. Right? And we use the right hand rule, right? You curl your hand in the direction of the current, and the thumb points in the direction of the magnetic field. Okay? Now what we want to do is we want to get an expression for the flux here, and then we're going to divide by the current, and we're going to get an equation for this inductance to determine what this inductance depends on. Okay, so the flux inside the inductor, remember, is the number of turns, N, times the flux in each turn, which is dA cosine theta. And in this case, the area, the loop is perpendicular, so the area is parallel to the field, so cosine of theta is 1, and the flux is just NBA, not to be confused with basketball. So then we plug in what B is, and B is mu naught I N over length, and you plug that in for the flux, the currents cancel, and we're left with an equation for the inductance. And so the inductance depends on the number of turns in the coil, and it depends on the area, the diameter of the coil, and it depends on how long the coil is. And so you see that the inductance, the value of L, is completely determined by how many turns you wind around this core and what the area of each turn is and what the length is. And so in other words, this value is fixed when the geometry is fixed, when you decide on the number of turns, the diameter, and the length, okay? And if we compare this, the capacitor also depends on geometry. The capacitance depends on the area of the plates, the separation, and the dielectric constant. So that also depends on geometry, just like inductance depends on the coil's geometry, okay? So the amount of flux that is in the loop divided by the current is a property of the coil geometry. And so if you want large inductors, you have more large turns per area. So the next thing that we want to do is derive an equation for the potential difference across an inductor. Okay, and if you remember the resistor, the potential difference across the resistor is the current times the resistance. Okay, what we're going to show is that the potential difference across the inductor depends on the inductance. Okay, just like with a resistor, it depends on resistance. But instead of depending on I, it depends on the rate at which the current is changing. So let's take a look here. So here you've got here's your coil, here's your inductor, and here's your current going through the coil. Okay, and if you curl your hands in the direction of the current, you see that your magnetic field points to the left. Okay, so your magnetic field lines point to the left. Okay, now let's try to increase the current. Okay, so now we increase the current, and we're going to increase the magnetic flux through the loop. Okay, so the magnetic flux, remember, is going to the left, and now we're increasing it. Okay, so Snell's law, Lenz's law says that that's going to induce an EMF, meaning the magnetic field induced will be in the opposite direction as the original field because it wants to oppose this increase. It wants to slow down the change in flux. So the induced magnetic field will point to the right, okay? And that corresponds to a current which is going in this opposite direction. So this, as long as the flux is trying to increase, meaning you try to increase the current, this magnetic field is going to try to oppose that change, okay? And since the current is movement of positive charge, basically what that means is that this carries positive charges over to this side of the coil and negative charges stay here. And so the potential difference is in this polarity, okay? So in other words, if you're going through the coil, you're going to lose potential going across the coil. It's more positive here, less positive here. You're going to lose potential while the current is increasing. You're going to drop voltage, okay? Now similarly, if you decrease the current through the coil, that means that this flux to the left is decreasing, okay? And so what's going to happen is that induced magnetic field is going to point in the same direction as the original because it wants to minimize that reduction, so it's trying to help it out here. And that gives rise to a current going in this direction, which pushes the positive charge over here. And so now, for decreasing current, you get a gain in potential, meaning you're going from less to more positive as it goes across the inductor. Okay, so that's why you only get a potential difference across the inductor when the flux is changing. Okay, if the flux is not changing, meaning the current isn't changing, you don't get any voltage lost or gained across the inductor. Okay, now mathematically this is pretty easy. If we plug in that the EMF in a coil is the negative rate of change of the flux, and the EMF is just the potential difference measured across the coil. Okay, now we plug in that, recall that the inductance L is the flux divided by I, and so the flux is Li. We plug that in. L is a constant, and we get that the potential difference, or the voltage drop across the coil, is negative L di dt. Okay, and so this, after all the bells and whistles, this is the equation which gives us the potential difference across the inductor. Okay, so let's take a look at this. If di dt is 0, meaning the current is constant, there's no EMF. Delta VL is 0. Okay, that's why for DC circuits with a constant current, there was no point talking about inductors. They don't do anything, okay? It's only when the current is changing that you get a potential drop across the inductor, okay? So let's look here. If the current is increasing, meaning di dt is positive, that's a positive number. Inductance is positive. The potential delta VL is negative, okay? In other words, if we're going in the direction of the current, delta VL, the voltage drop is negative, meaning we're going from high to low. We're losing potential, okay? So if the current is increasing, the potential decreases as we go along the direction of the current, just like with a resistor, okay? If the current is decreasing, di dt should be less than 0. di dt, I'll fix that. If di dt is less than 0, this is negative, L is positive, multiplied by a negative. If di dt is less than 0, the potential increases as you go across the coil in the direction of the current, okay? So that's why it's easier just to look at this equation, and the potential difference is the opposite in sign of di dt. So let's do an example. So suppose we have a 10 millihenry inductor, so 10 to the negative 2 henries, and that's L. And suppose that the current drops from 150 milliamps to 50 milliamps in 10 microseconds. Okay, so the question is, what is the potential difference? What's the voltage drop across this inductor while the current is decreasing? Okay, so let's look at what we know. L is 10 millihenries, which is 10 to the negative 2 henries. Now we got to calculate di dt, or change in current over the change in time. Okay, final current is 50 milliamps. Original is 150, and so the change is negative 100 milliamps in a time of 10 microseconds, which is 10 to the negative 5 seconds. Okay, so we plug that in for di dt, and we get that delta VL is 100. It is henries times amps per second. Okay, and then you can go through all the unit tricks here and show that that's equal to volts. Or in other words, the potential difference across the inductor while the current is changing is 100 volts. Okay, so to calculate the potential difference, again, we multiply the inductance by the change in current, which is final minus initial current, divided by the time interval, and then we tack on a negative sign, okay? And since di dt is negative, current is decreasing, the potential difference is positive. So in other words, you would gain potential. It would be the opposite of this, meaning we would gain potential in going across the inductor. And so if you turn the current on and off, like for example, if you open and close a switch and you have a coil and you get very large changes in current, you can get very large voltages across the coil. And these can be used, for example, to generate these large short voltage pulses needed in spark plugs in other circuits. For example, you need a very large short pulse of voltage to ionize the air, right, to break down the air and to cause a spark in a spark plug. Okay, and so here's an example. Okay, if the switch is closed and everything is just sitting here and I is constant, and di dt is 0, and you get no voltage drop across the coil. Okay, now suppose that we open the switch. So in other words, you're turning the current off almost instantaneously, right? It starts off with a value I, ends up with 0. So you get a large negative di dt when you open this switch. So what does that mean? If di dt is large and negative, then you're going to get a large positive delta V, which means a large gain in potential across the coil. Okay, and if di dt is very large, meaning you turn it off and almost instantaneously, you can get a huge voltage across the amp, okay, across the coil. And so that's used in spark plugs and other circuits. So that's one application of inductors is when you have a change in current that's very fast, you can get huge voltages across this coil. And what this is sometimes called a choke. So the final topic, and I'm just going to give the result, and there's a homework problem in it. Is we said that the inductor stores energy in its magnetic field. Okay, so in other words, it's like an energy bank, and it's a lot like a capacitor. Remember, the capacitor stored potential energy 1/2 times C times the square of the potential difference across the plates. You can derive that the energy stored in an inductor is, again, 1/2, and instead of C you have L, and instead of potential difference squared you have I squared, and so an inductor stores potential energy in between the plates, and that's equal to 1/2 Li squared. So it behaves a lot like a capacitor. It stores energy, only it's stored in the magnetic field instead of in the electric field. So I encourage you to work out example 3014, and there's more problems on homework 12 related to this. So let's go back and look at what you should know since we're done with the notes here. So you should be able to sketch an AC generator and explain how the rotating coil generates the nth. Okay, you should be able to sketch that. You should be able to start with Faraday's law and derive the equation for the nth in the coil, which is just right here. It's just taking a derivative, and show that it depends on these factors. And you should be able to apply this equation to an example similar to example 1. Okay, so you should be able to do that. You should be able to sketch a transformer and state its function. Okay, its function is to change the voltage, either stepping up or stepping down. And you should be able to apply the equation relating the number of primary and secondary turns to the voltages and currents. Okay, and that's pretty easy. And then you should be able to state what the purpose is in using step-up transformers to increase the voltage generated at a power plant before transmission, and why step-down transformers are used to decrease the voltage at the access points, the residential access points. You should be able to state what an inductor is and calculate inductance based on the geometry. So in other words, if you're given the number of turns, the length, and the diameter, you should be able to relate the nth, the potential difference across an inductor, is equal to L times di dt with a negative sign. So you should be able to relate that to changes in current, similar to the last example. And you should be able to calculate the potential energy stored in an inductor's magnetic field. Okay, and so there's homework problems that should prepare you for the exam for this. So that is pretty much it as far as the new material in the course. So remember, next week is, what do they call it, wellness days, and so there's no new material, but you should begin to review for the final, and you should come to office hours with any questions. So that's it. I am heading to bed now. It's late at night. Have a good night.